I want to talk about transitions between the three different phases of H2O, liquid water, ice, and water vapor, because these are really important in hydrology. First, we should name them, as shown on this diagram. And most of these terms are probably familiar, such as evaporation for the transformation from liquid water to water vapor, but others might be new. It's actually not that important that you memorize the new terms, but we do need some kind of common language so we can discuss why these processes are important. Here's one of the main points. Some of these transitions are easier than others. What I mean by easy is that they will occur whenever thermodynamics favors one phase over another. For example, as soon as the air becomes undersaturated with respect to water vapor, water will willingly and quickly evaporate from liquid water and enter the atmosphere. There is no impediment to this process. In contrast, when water becomes oversaturated with respect to water vapor, it's actually difficult for that excess H2O to transform into liquid water. This means that under some conditions, the atmosphere might contain, more than its saturation level of water vapor because the water vapor can't manage to transform into liquid water. It's hard. We call this state oversaturation. There are two main reasons why some processes are difficult, and the first has to do with the structure of the three different phases. Gases are, of course, loosey-goosey, with molecules zooming all over the place, while the molecules in solids occupy rigid positions. Water is sort of in between. So one observation that explains why some transformations are difficult is that it's hard to go from a loosey-goosey state to a highly structured state, because this requires the highly energetic molecules to settle down and clump together. Notice that all the processes that transform to a more structured state of matter are difficult, and all the processes that go in the opposite direction, from more structured to less structured, are easy. You can see the problem with transforming to a more structured state in this simulation, which shows water slowly crystallizing to ice. Notice how the water molecules need to be positioned in exactly the right place to attach to the growing ice crystal, and that this takes time. Actually, there's one other thing that I want to point out about this simulation, which has to do with the overall level of energy of the two phases. Both the water and ice are at the same temperature, but the water molecules are obviously vibrating more violently. This violent vibration is the result of the water molecules having more energy. The molecules in the ice are much less mobile, just slowly vibrating in place, and we can thus conclude that the ice molecules have less energy. The transformation of water to ice then must end up releasing the excess energy of the water molecules. The molecules need to shed energy in order to slow down and become fixed in place on the growing ice crystal. Again, remember that this process is happening at a single temperature. The energy released when water transforms to ice is called the latent heat of fusion, and similar energy transactions occur when H2O transforms between any of its three phases. When water vapor transforms into liquid by the process of precipitation, it too must shed excess energy. This is the latent heat of evaporation. You don't need to memorize all these terms, but you should be able to predict whether a transformation will release energy, called exothermic, or consume energy, called endothermic. Transformations that go from a high energy state to a lower energy state must release energy, while transformations that go from a low energy state to a higher energy state must consume energy. As long as you remember that gas molecules have the highest energy and solid molecules have the lowest energy, you can figure it out. Remember I said that there were two reasons that some phase transformations are hard, and now it's time to talk about the second reason. Let's consider the transformation from water vapor to liquid water. By the laws of thermodynamics, this process will occur spontaneously whenever the energy content, formerly the Gibbs free energy, of the liquid water is less than the energy content of the water vapor. Spontaneous processes go towards lower levels of Gibbs free energy. In this diagram, I've shown that if we replace the pool of water vapor with a pool of water, the Gibbs free energy will be reduced, and this is thus a process that ought to occur spontaneously. But in real life, we don't just produce a pool of liquid water. We produce small water droplets. The collection of water droplets might have a lower Gibbs free energy than the pool of water vapor, but there's a problem. The water droplets have collectively an enormous surface area. We call the formation of independent spheres of water homogeneous nucleation. The problem with homogeneous nucleation is that the droplet surfaces are regions of high energy. Bonds are stretched on the surface in order to accommodate the interface between water and air, creating tension and energy. This additional surface energy must be included in the total energy transaction between water vapor and water droplets. Again, remember that spontaneous processes move to reduce total energy, and if the process produces a large amount of surface energy, it may no longer be energetically favorable. But sometimes we can get around this obstacle if there are pre-existing substrates onto which the water can precipitate. We call this heterogeneous nucleation. For example, in the atmosphere, there are many tiny solid particles called seed nuclei. These might be dust particles, pollen grains, whatever, but they have the effect of offering a soft landing place for the water vapor molecules to attach without generating a huge amount of surface energy. So even though some additional surfaces are created when water precipitates onto the surface of the seed nuclei, it's still much less than the energy that would have been the result of all those tiny water droplets, and this may therefore permit the process of transformation to occur. So, to summarize, in the absence of surfaces of solid substrates that allow heterogeneous nucleation, homogeneous nucleation must occur, which produces a large number of small water droplets with collectively a large surface area and a large additional energy. This additional energy may make it energetically impossible for the water droplets to form. They won't form if the transformation results in a net increase in energy. In this case, the air can be oversaturated with water vapor, but there's no easy way to get the excess water molecules out of the air and onto water droplets because the required surface energy is too costly. On the other hand, if seed nuclei are available, or blades of grass or trees or whatever, then there's only a small energy cost of precipitation, and water will readily transform from water vapor to liquid water whenever thermodynamics gives it the green light. Incidentally, you should now be able to explain why dew forms on blades of grass or plants in the early morning. As you will learn, cooling air becomes increasingly saturated with water vapor until it reaches saturation and even becomes oversaturated. Homogeneous nucleation is difficult, but heterogeneous nucleation on the surfaces of the grass is easy, and this is how the oversaturated air sheds its excess water vapor.